So welcome to the very last video in the rotation and torque topic. I would be guessing by now that you have had enough new equations to make your head spin. And in this short video, I will be giving you the very last one. In this video, we'll be looking a little bit further into angular momentum. In particular, we'll be looking at the relationship between angular momentum and inertia, and at the conservation of angular momentum. So if we start with a top view of a spinning, we know that a particle, represented by our dark purple circle somewhere on that disk, is moving with a tangential velocity v, and we know that the linear momentum of that piece is equal to r cross p, where r is our radial vector and p is the linear momentum. And we know that we can also write that using this equation, once again converting from our linear velocity, our tangential velocity, to our angular velocity. We know that v equals r omega, and in this case we are also referring to the component of r that's perpendicular to the velocity, and that gives us that our angular momentum is equal to m r squared omega. To find the total angular momentum of the disk, we're interested in the entire area, and we find that by summing all of the individual angular momentums of the individual parts of the disk. And when we do that, we find that our total angular momentum is equal to the sum of mr squared times omega. We know that our omega, our angular velocity, for every part of that disk is constant, because every part of that disk makes its rotation in the same time period. And we also know that the sum of mr squared for each individual component gives us the total angular inertia for our disk. So substituting those two values in, we can find a very nice equation for our total angular momentum as I omega. The proof of this equation follows a similar line to how we derived the formula for the rotational kinetic energy, and I'll leave it up to you whether you would like to attempt it or not. There is a full derivation in the course textbook. Our final topic for discussion in this rotation and torque topic is the conservation of angular momentum. And so we know that the conservation of linear momentum is a very powerful problem-solving tool for us and allows a very simple procedure for solving what are technically very complicated problems. So as an example, we can find the outcome of a collision knowing only the initial mass and velocity of each of its components and knowing nothing about the actual collision itself. So knowing whether or not angular momentum is conserved would provide us with an equally powerful tool in a rotational sense. And so the short answer is that yes, so angular momentum is conserved. So that means that at any point in time in a system, in a rotating system, the total angular momentum of that system is constant. So the initial angular momentum is equal to the final angular momentum for any 2 points in time. And as a final question, here we have the Japanese figure skater in the Russian Winter Olympics. And my question to you is, what will happen to her angular velocity when she spreads her arms out wide? If you'd like a hint, then keep watching for the next few seconds. And if you'd like to try the question without a hint, then I suggest that you stop the video now. So my hint is that you will need to use the equation that you found in the previous slide, that the total angular momentum is equal to I omega,